So copper 2 chloride, and I wrote aqueous. Now, as soon as you see aqueous, that should make you think, I'm going to need to rewrite this as what you would see in the beaker. Then let's say that was reacting with sodium hydroxide solution that was also aqueous. Okay, so what's going on here? If I told you this and said it makes CuOH2 solid and NaCl aqueous, I'm kind of telling you what happened. Well, for us to do math and determine things, we would have to have starting amounts, but we'll have to convert the starting amounts and the equation to something we're more used to. So let's say, for example, you had 15 milliliters of this at 0.100 moles per liter, and just to pretend you had 25 milliliters of this at 0.200 moles per liter. Okay, so we want to do stoichiometry. In my class, when you say aqueous, what are you supposed to do? You're supposed to rewrite everything as ions. So that actually becomes copper 2 ions. I knew it was copper 2 ions because there was 2 chlorides, and for this to add up to 0, and they're -1 each, that had to be +2. There were chloride ions. Now, there were 2 chloride ions. I'm not going to bother writing them both because I'm not going to need to balance this equation yet. So I'll just list the things that are there. So here's a list. There's also, in the beaker, sodium ions, and there are hydroxide ions. Okay, so here's this beaker, and those 4 ions are present inside the beaker. And we're saying that for some reason, these 2 ions, Cu and OH, stick together and make a solid. Okay, and that means water is unable to hold those ions apart for some reason. And the sodium ion and the chloride ion, because it's aqueous up there, must still be separate ions. So what are the spectator ions? Well, it looks like sodium ions didn't do anything and chloride ions didn't do anything. So let's write our net ionic equation. That's the one that should be balanced. Copper 2 ions and hydroxide ions make CuOH2 solid. Well, look, there's 2 hydroxides, so I'll need 2 hydroxides. Now I have a balanced net ionic equation, and in my class we will do all our math from that point because that's the point that tells you what's really reacting. So the sodium ions and chloride ions up here, they would just remain floating, but eventually what you're going to get is the water with the spectator ions. So there'll be a bunch of sodium ions and there'll be a bunch of chloride ions. There'll be a pile of stuff on the bottom if you let it sit or if you filter it or spin it down. That stuff on the bottom will be copper 2 hydroxide. And depending on which one is left over, there might be some of those ions up there. Okay, so let's look at what we had for starting amounts. We had this amount for the copper 2 chloride. Let's determine how many copper ions were actually in our container. How would you do that? Well, 15 milliliters, 1,000 milliliters per liter. Each liter of that was 0.100 moles of CuCl2. If I take those apart, each mole of CuCl2 becomes 1 mole of copper 2 ions, and I get, let's see, 0.001536 moles of copper 2 ions in the container. Okay, this last step is how you take and determine instead of copper 2 chloride, which doesn't even exist in the container, how many actual copper 2 ions. That number goes right here. That number is 0.00150 moles. Okay, now let's see how many hydroxide ions there are using this information. So I'd go 25 milliliters. I would do the same math, and at the end I'll get what did I get? 0.00500 moles of hydroxide ion using virtually the same math as that with different numbers. Okay, so there's my 2 starting amounts, 0.00500 moles of hydroxide. Well, hydroxide is getting used up faster, but it looks like there's still not enough copper. So let's prove that. How would I prove that? I would say 0.00150 moles of copper 2 ions, to be more specific, and each mole of copper 2 ions requires 2 moles of hydroxide ions, and so that would be 0.00300 moles of hydroxide needed, and I have 0.005, so I do have plenty of hydroxide. Therefore, the copper is what runs out, and when I'm out of copper, I can't make any more of the copper 2 hydroxide, so I'll use copper 2 ions as my stoichiometry. To get this number here, I would have the starting amount, 0.00150 moles of copper 2 ions, and then I would say a, let's see, 1 to 1 mole ratio, 1 to 1, and I would get that many moles of copper 2 hydroxide formed. Okay, what kind of reaction was that? When you have two ions and then water can't hold them apart for some reason. Well, that was called the precipitate reaction, which we have abbreviated PPT. Okay. Now, one little side note about precipitation reactions. If you have a container, so this is what we determined. There's the beaker. You had sodium ions floating around. You had chloride ions floating around. On the bottom, we had a pile of copper 2 hydroxide that was a solid, and we determined that in the previous math that the copper 2 ions ran out, so there are a few hydroxide ions still up in solution. There's a picture of what's left in the solution, and we could actually figure out how many grams of the solid there should be. Okay, now in real life, does every single copper 2 ion stick to the hydroxides? No, because some of them redissolve, and then you eventually get a position where as soon as you get some copper 2 ions up here, they start to stick to other things, and we have that equilibrium situation where the rate at which they're reforming equals the rate at which they're dissolving, and that makes it much more complicated. So technically, not all of the copper's down here, but since we called copper 2 hydroxide insoluble, well, what that means is that at equilibrium, the amount of copper 2 ions up here is so small, we're going to ignore it. In fact, we're going to assume that all of them stuck together with hydroxide and are sitting on the bottom. Okay, because otherwise we can't do stoichiometry. Stoichiometry requires that one pile runs out, and when one pile runs out, you stop making the product. Okay, our last kind of reaction was something like this. HCl aqueous, which we learned is called hydrochloric acid, reacts with sodium hydroxide aqueous, and we said it makes H2O, which is a liquid, and NaCl aqueous. Okay, so we see aqueous. What's the first thing we do? We rewrite the equation so that we can list things as they really appear. Now, hydrochloric acid is a strong acid. That means when you put it in water, you get hydrogen ions and chloride ions, and they completely break apart. This sodium hydroxide is aqueous, which means you get sodium ions and hydroxide ions, and we're going to make some stuff. Oh, look, that one's aqueous. So that means we're not actually making solid sodium chloride, we're making salty water. Well, we had salty water when we started. Let's see. H plus and Cl minus, that's how you write hydrochloric acid when it's aqueous. And then you have sodium hydroxide, which would be Na plus and OH minus. And we're saying the H plus and the OH minus stick together to make water. And let's see, that's aqueous right here. So I'll write Na plus and Cl minus. Nomenclature is very important because you need to see this as pieces when they're made of ions. Okay, so what are the spectator ions here? Well, sodium didn't change. Chloride ion didn't change. Really, the only things that are reacting are H plus and OH minus, and they make H2O. There's our reaction. Now, in our class, the math problem that we did with that was a titration. Okay, and we were trying to determine the molarity of the H plus. So what did we do? We said, well, when we started, we took some volume of hydrochloric acid. Let's just pretend it was 25 milliliters. Okay. Now, what am I trying to find? If I'm trying to find the molarity of H plus, I need to make a fraction. And on the top, I need the moles of H plus, and I need the liters of H plus. Well, there's the liters if I convert it. So that number is going to go right here, except I'll have to make it liters, which means that'd be 0.02500. I just need to figure out how many moles of H plus there are so that I can divide them and get the moles per liter. Well, how did we do that? Well, we said, let's use sodium hydroxide and put an indicator in, and when all of the H plus is gone, we used phenolphthalein, so when there was leftover hydroxide, it turned pink and stayed. So let's just pretend for this situation that it took 30 milliliters of 0.150 molar sodium hydroxide. Okay, what can I figure out? Well, I'm trying to find out how many moles of H plus there were. This information I can use to figure out how many moles of OH minus it took to cancel out the H pluses. Because at the end point, we'll assume that the OH minuses and H pluses were the same amount. So how do we find this number here? Well, 30 milliliters. Let's see, 1,000 milliliters per liter, and each liter is 0.150 moles of NaOH. And we would do the one extra step to determine the moles of hydroxide like we've been doing, and that came out 0.00450 moles of hydroxide. Okay, that means at the end point, when we just ran out of hydrogen ion, it took this many hydroxides. Well, in a titration, we'll assume that since this is 1-to-1, that must be how many hydrogen ions there were. So we can say 0.00450 moles of hydrogen ion because we're saying at the end point those are equal. That means in my original 25 milliliters, there must have been 0.00450 moles of hydrogen ion. And if I divide those, then the original molarity of the hydrogen ion must be about 0.18036 figs moles per liter, which in our class we converted to pH. Why is that an acid-base reaction? It's an acid-base reaction because of this right here. The net ionic equation shows H plus reacting with OH minus. In our class, that's an acid-base reaction.